Hi everyone. Today we'll begin our discussion on new chapter, which is bending deformation. Bending deformation lecture will be composed of 4 lectures, and today will be the first out of 4 lectures. Before talking about bending, because we have already went through the axial loading and torsional loading, let me give you a recap on the overall flow of this lecture. So some of you who are very good at organizing everything, you might get, I would say, boring about hearing the big picture again and again. But I think for a majority of you, it is really important to have big picture and the entire logical flow of this entire lecture. And I'm gonna try to give this big picture overview again and again. Okay. Yeah, sorry for some of you who feel boring about this, but yeah, I'm sure that it could help you to make a overall structure of the entire lecture. So please do not stick to a specific homework problem, specific a sample problem, specific chapter. Whenever you take any major courses, please try to have overall structure in the viewpoint of the professor or lecturer. Okay, so that if you have a big picture, even though you forget every little tiny detail after midterm exam and final exam, you can still search for your textbook because you have the overall structure. But even if you don't have overall structure, even though you have good scores in midterm and final, after the semester is over, you're gonna forget everything. Yeah, I'm sure about it. So yeah, please try to have a big picture by yourself. Even though I give you this overall big picture lecture, yeah, please try to draw this logical flow diagram and try to have your own big picture in ME231, and same for other courses. Okay, so as I told you, our course is about obtaining the deformation due to the external loading, and based on that deformation and stress distribution, we want to enable reliable design. And what I mean by reliable design is the maximum stress in the structure must be smaller than the material property, which is given as the allowable stress. Okay, so to do so, what we have to do is following. So suppose that we have a structure adhered to a rigid wall, and there can be axial loading, torsional loading, and bending, and pushing from the top, and etc. Okay, there can be many different loadings: vertical loading, horizontal loading, torsion, and bending. This is torque about this axis. Okay, now given this kind of axial loading, for any point of the body, you can make an imaginary cut, and at the imaginary cut, with respect to the centroid point, you can define normal force reaction, vertical force reaction V, and torque about g-axis. This is x, y, and g in our notation, and torque about the x-axis, okay, which is torsion. Okay, so these are 4 reactions you need to make a mechanical equilibrium when you subject to external forces and torque, which is given as this. Okay, so until now, what we have covered is given pure normal loading, and given axial loading, given torsional loading, pure torsional loading, pure axial loading, we are able to obtain normal stress and shear stress, and we defined what is J. Okay, so this is what we have done, and the remaining part will be covered today and the lectures that follows today's lecture. Okay, so the overall flow, logical flow is as follows. So we have to first solve a statics problem by free body diagram. Actually, this is something that is not covered in our course. You should have mastered drawing free body diagram and solving statics back in freshman physics. However, even though you're not able to master free body diagram and statics problem in freshman general physics, you still have opportunity. If you try to solve all sample problems, and if you solve all homework problems by yourself, anyway, you have to get a lot of practice on drawing free body diagram, and you're gonna get used to it. Okay. Anyway, so after solving free body diagram and statics, you're gonna obtain reaction force, which is N and V, and reaction torque, torsion, and a moment M. Okay, and given these kind of reaction force and torque, what you're gonna do is you're gonna get normal stress out of N and out of M. You're gonna get shear stress out of torsion T and out of the shear force V. Okay, and having obtained the normal stress and shear stress distribution, you can get strain using material property. Okay, so given normal stress and given shear stress, you will be able to obtain normal strain and shear strain out of generalized Hooke's law. Okay, and in utilizing generalized Hooke's law, you're gonna need the material property, and we found that out of 4 elastic constant, only 2 of them are independent to each other, and the other 2 can be obtained automatically using the relationship if 2 of them are given. Okay, having obtained the normal strain and shear strain, after integrating this for entire body, we can obtain either displacement or angle of twist, so that we can predict deformation. Okay, so this is the logical flow. So in the end, we're gonna predict deformation, and as we move to the final step of predicting deformation, because we're gonna get normal stress and normal strain, we'll be able to compare the maximum normal stress and maximum shear stress, and check if maximum normal stress and maximum shear stress is smaller than allowable normal stress and allowable shear stress. Okay, so that this can be considered as design of mechanically reliable structures. Okay, so these are the overall flow of our lectures, and when you look at the equations for M and sigma, equations for V and sigma, you're gonna see that we still don't know what is I and what is T, and that will be the topic of this chapter and the chapter that follows this chapter. Okay, so please try to have this overall picture. Through ME to 3-on, we predict deformation. Through ME to 3-on, we try to design mechanically reliable structure, and based on this practice, we can make really safe structures, so that we can save people's life and preventing huge safety accidents. And that's the purpose of doing ME to 3-on, and that's the one of the purpose of being mechanical engineers. Okay, so having this in mind, let's move on to real meat of today's lecture, which is new topics and new concepts.